Hello, my name's Quentin McKellar. I'm the Vice-Chancellor here at the University of Hertfordshire, and it's a great pleasure for me to welcome all our engineers, maths, science and technology association members to the annual Prestige Seminar. Of course, these subjects are incredibly important, particularly with the challenges that we currently face, the challenges which exist in delivering a healthy environment, the challenges in creating vaccines, of course the enormous challenges to our economy, which are underpinned by engineering, maths, science and technology, and of course the extraordinary challenges to our environment which still currently exist. It's of course really important for a university like the University of Hertfordshire, which has evolved from the technologies which underpin the aircraft industry. Of course, we emerged from the de Havilland aircraft business, and indeed some of our campus is still based on the old de Havilland aircraft site. The seminar which you're attending is now in its 21st year, and I'm delighted to say that each of the seminars have been held at the University of Hertfordshire. But given that technology is such a critical part of your seminar profile, it's marvellous that this is the first seminar which is being done entirely virtually, and that's using, of course, the appropriate technologies which have been developed by people like you for this purpose. Of course, you have this year got the most fascinating topic on space debris. It's a topic that I know very little about, but I was hugely interested to read your flyer to learn that there are 100 million bits of junk in space orbiting Earth, and they're traveling at 17,500 miles per hour. Truly extraordinary. I have to say I'm particularly relieved to know that you, during this seminar, are going to work out what to do with all that junk and how we're going to ensure that it doesn't impact negatively on the way that the Earth works. I hope that you have an absolutely fabulous and incredibly exciting day, and it's my pleasure now to welcome the chairman to your first session, Martin Coleman, and Martin's going to look after you during that session. So thank you very much for your attention. Thank you very much for attending and attending in a virtual sense at the University of Hertfordshire this marvellous seminar.
Thank you, Quentin, for your welcome and generous support. Welcome to EMSTA's annual seminar. Before I begin the seminar on the subject of space debris, let me introduce you all to EMSTA's chairman, Roger Body. Roger, over to you.
Thank you, Martin, and thank you again, Quentin, for your welcome address. Hello, everyone. I'm Roger Body, chair of EMSTA CIC. EMSTA is an input group focusing on STEM activities. Our aim is to encourage young people to consider careers in engineering, maths, science, technology, and the arts. And you can find out more about us from our website at www.emsta.org.uk. We work closely with other STEM-facing organisations and professional institutions to address STEM topics. EMSTA's link with the University of Hertfordshire has been built over the last 21 years through this series of annual Prestige seminars, and we are delighted to maintain our link with Professor McKellar's welcome address this year. To date, we have probed the cosmos through the eye of the Herschel telescope, travelled to Mars with Beagle 2, and questioned whether man or machine should go to Mars. We've journeyed to the depths of the oceans to study marine biology, excavated the tunnels of Crossrail, questioned our misuse of fossil fuels, and debated investment in sustainable energy. Normally, we do this in the splendid surroundings of the Western Auditorium at the University of Hertfordshire. However, these are not normal times. And having chosen our subject, press-ganged Martin into chairing the event, and assembled a panel of world experts, we are about to boldly go where no hand has set foot and use technology, yes, technology, to present this year's seminar within the constraints of COVID lockdown. True to EMSTA's aims and objectives, our panel is a young panel comprised of young people and has an average age of 37. They're all at the top of their game. Their presentations have been pre-recorded and these will be followed by a live panel discussion to address questions raised. So please, if you have questions, leave them in the chat room for our review and collation for the question and answer session later this afternoon. Before we address those questions, we will invite a Hertfordshire school pupil nominated by the Arkwright Foundation to accept an award for outstanding achievement in STEM-related studies. This entire event is being recorded and, including presentations, will be made available to all those who have registered and for onward distribution to relevant organisations, international institutions, academia and schools, and other partnered STEM schemes. Well, that just about sets the format for the event. And I now have pleasure in handing you back to Martin to steer us through what promises to be an eye-opening discourse covering technology, science, engineering, maths and ecology, supported by graphic art and some brilliant cinematography that we have called Space Debris 2020 Vision. Martin, the floor is yours.
Thank you, Roger, for that. And I'm feeling younger already, so that's a good start. Okay, so on to space debris. Space debris and space traffic management are the space challenges that face us now. They're at the forefront of most discussions taking place within our satellite industry. And with more satellites being launched into space, space situational awareness is more crucial than ever to protect those assets in space. And that's difficult to perceive or even think about down here on planet Earth. So we're hoping this session opens the doors and shows you what space truly looks like right now. And some of it will be live and you will see where satellites are positioned in space. And I think you will be, if nothing else, surprised with what we're about to discuss and the problem. But before I get there, I'd like to show a short video just to set the scene for us all and make a comparison to something that's close to our hearts here on Earth. We know more about the plastic problem here on Earth, and I hope that video helped show the problem we have created in space, really unseen. We can't see it, not easily from down here. And it's certainly not on the, shall we say, our politicians' horizon. So this panel brings together subject experts on space debris and its management. And this doesn't have a happy ending, this story. This story is real. It's a real problem, just as is plastic in our oceans and elsewhere. This is a big challenge. So this seminar won't answer and have a resolution that we can all smile about, but it will tell the story truthfully, and we will get the real facts behind this, that we can start that discussion and create more discussion. It needs pushing. And the people we've got on this panel do a lot of work to try and fix this problem. So we're highlighting new technologies, we're exploring how to monitor and maybe even resolve the problem of debris. The session looks to the future, how better to manage a constellation, a low or medium Earth orbit environment, and protect the larger geostationary Earth orbit satellites that have been there for many years and are probably the most important part of our space ecosystem. And we talk about protecting those assets, the environment of space itself, and possibly the processes and maybe the regulation we need in place, international regulation we need in place to do this. So without further ado, let us start the session. Well, first of all, a big thank you to our panel of experts who have given their precious time to make this seminar possible. First of all, I would like to start with Mariba, and I want Mariba to help us set that space debris scene. So Mariba, welcome, and over to you.
Yes, no, thank you very much. So right, Mariba Jah here at University of Texas at Austin, Associate Professor of Aerospace Engineering and Engineering Mechanics. And just very briefly, my background is in studying and understanding motion of objects in space. I started off working at NASA's Jet Propulsion Laboratory as a spacecraft navigator for Mars missions, but then I made a shift and worked for the US Air Force Research Laboratory, where then I became acquainted with the current space traffic problem and come to realize that, wow, there's over 20,000 things that we keep track of that are zipping past each other in different orbits. And I'll show you this here in a little bit. And interestingly, I came to understand that we have a lot of space traffic and we don't have space traffic rules that we've all agreed upon. So that's part of the issue. And so, now that I'm here at the University of Texas at Austin, I'm really focusing the work to try to address problems related to space safety, space security, and space sustainability. Examples of space safety problems are we try to avoid things colliding with each other on orbit, people hopefully being able to get out of the way to keep space services and capabilities that we depend upon on a daily basis from being lost or from being disrupted or degraded. So from a safety perspective, we want to do that. From a space sustainability perspective, really interested in making some ties to environmental protection in other domains. And so by and large, most environmentalists focus on oceans, atmospheres, and climates, not and space. So we want to include space in that because near Earth space is a finite resource, which I'm going to show you what I mean by that. And so much like we have anthropogenic objects or human-derived objects that pollute these other areas, oceans, atmospheres, and climates, we also have anthropogenic objects in space. So I call them now anthropogenic space objects. And what we'd like to be able to do is, in extending these environmental protection narratives to near Earth space, we'd like to do two things. One, can we come up with a global definition of orbital carrying capacity? So every given environment has a capacity of being able to sustain individuals in that environment, whether that is an ecosystem where birth and death rates affect that carrying capacity. The ecosystem being finite can only support so many individuals using that resource, right? And when it comes to things like highways have a carrying capacity as well to maintain safe traffic. So like the highways and like the ecosystems, these anthropogenic space objects, there is a birth rate, which is now highly significant because it's increasing exponentially. The death rate is very low as compared to the birth rate. And so there's a preponderance of more individual anthropogenic space objects on this orbital highway. And we'd like to be able to define this carrying capacity so that we can then use that carrying capacity within licensing and policy type things, because that capacity, there's no ownership of it. We should be stewards of the capacity as a global community. And we could say, well, much like the ITU allocates certain frequency spectra to satellites, we should have an analogous international organization that could then allocate capacity, orbital capacity, to different entities in a shared way. And anybody using the capacity, whether it's SpaceX or anybody else, understands that it's leased. Humanity is leasing this capacity to you, and with the intention that you give the capacity back when you're done. Much like we try to minimize single-use plastics on the Earth, I'm advocating for minimizing single-use satellites. And so looking to recycling and reuse of satellites and that sort of stuff to the greatest extent possible. So now you understand a little bit about this sustainability perspective. The last S in the 3 S's is security. And some people believe space security is uniquely a geopolitical thing. And I say not so much. Any environment of human activity has always suffered malicious behavior, malicious intent. And so, you know, company A, company B are very competitive. It's a mostly unmonitored environment. People can get away with things. You better believe that that's happening. To believe that the space domain is an area of pure benevolence, kumbaya, and basically, you know, having pillow fights and tickling each other is ridiculous. Like, that's not the way it plays out. And so we need to do a better job of monitoring, quantifying, assessing how people are behaving, and be reluctant to just call anything we don't understand malicious intent. We have to put things within a cultural context to understand what is normal behavior for different entities in space. I can tell you, and I'm going to show you, that we have a number of treaties: Outer Space Treaty, Convention on Registration of Space Objects, Liability and Damage. These things are not interpreted in the same way by all these countries. Even though they sign the same document, it's interpreted differently. And we need to understand those things. So this kind of sets the tone in the safety, security, and sustainability. You might ask me, well, how do you measure yourself in the work that you do against the 3 S's? And the way that I measure myself is, I ask myself the following question: does any of my work make the domain more transparent? In other words, what's up there? Who does it belong to? What can it do? Does any of my work make the domain more predictable? Do I know how things are going to behave in a few hours, over the next few days, maybe weeks or longer? In any given scenario, how will any 2 entities actually behave? If object A is owned by the US and object B is owned by China or Russia, and they're going to come within 50 meters of each other, can I predict how these folks are going to behave? That is very important. And back to the treaty implementation, people interpret these things very differently. And then the last thing is, can I develop a body of evidence that can be used to hold people accountable for their behaviors in space? So those are my 3 measuring sticks: transparency, predictability, and accountability. So with that, I've said a lot of things. I actually want to show you some stuff just to put things into context. And of course, you know, as with all technology, nothing ever fails. So here we go. I'm going to share this with you. And so this right here is this crowdsourced database we call Astrograph that we've put together at UT. And this is just showing you dots which are not to scale, just kind of locations of opinions about stuff in space. So the sources into this are, you know, like US Space Command, Planet Labs, some data from Leo Labs, the Russian JSC Vimpel catalog, Amateur Telescope, CSAT-L, Maxar Technologies, used to be Digital Globe. I have to update that. Some of my own opinions, because I have sensors and I process people's sensor data. So anyway, that's kind of a conglomerate of opinions. But interestingly, just to give you an idea of why we need as many eyes on the sky as possible, this is the space traffic map that you would get from US Space Command. And if you said, okay, well, you know, what do the Russians believe? Wow, okay, there's the space traffic map. That doesn't quite look exactly the same. Indeed. And not only is there, let's say, some inconsistency or little overlap between some of these things, even for common objects, let's go and, I don't know, let's look at one of Planet Labs satellites, one of these 3U CubeSats, the Flock 1C10, for instance. And, you know, it's one satellite and there's multiple opinions on where this stuff is located. And we're just going to kind of try to zoom in here. Eventually, I'm going to hit pause because I want this to stop moving so I can actually make this comparison. But we have some simple two-body dynamics. I always like to invoke Johannes Kepler to simplify some of the motion here. And so, meaning that it's not real, it's just, it's fictitious, but just kind of rough order of magnitude. All right, so I'm just going to pause this right here and just kind of zooming in, but you can already see that there's some funny stuff going on here in the middle. And as I zoom in, you're going to see that the numbers are going to start becoming a little bit more visible. And so what I want to show you is this, right? It's like, okay, here's the flock 1C10, and these orbits are very close to each other. So that's good news. But number one is where the public catalog from the DoD says that object is approximately. Number two is where the owner says it is. Number three is where Leo Labs believes it is based on its radar data. And number four is where I believe it is based on Leo Labs data. So the thing is, one object, four opinions. Even when I process the same data as Leo Labs, I get a different answer. Why is that? Because my assumption in the physics is different, because the algorithms that I use to infer the orbit is different. So people just need to realize the power behind crowdsourcing and that sort of stuff. Why do we want to do this? Isn't it a problem that we have multiple opinions? Well, if you have too few opinions, it could be. But the way that you know that you have the world's most accurate clock is you have hundreds of them. And so the thing is, you want as many independent opinions about stuff as possible so you can try to find the consensus, the barycenter of the opinions, to try to figure out what's best. If I tell you, move out of the way because you're going to get hit by flock 1C10, after seeing this, you'll probably say, well, move out of the way based on what? 1, 2, 3, or 4? Because the answers are going to change, right? The probabilities of collision are going to be different for all four of these things. This is just to underscore to you the importance of combining data, of fusing data, of understanding its pedigree, its veracity, all these things. These are critical things. All right, I don't want to take too much more time. I do want to show you this very quickly. So you might say, how busy are things, on orbit, kind of crisscrossing each other? Well, so there's this thing that's called the conjunction streaming service that we put together. It's just taking the public catalog. You can see almost 20,000 objects are being screened across each other. And the question that we're asking is, over the next 20 minutes, which pair of objects is predicted to come within 10 kilometers of each other, just over the next 20 minutes? I can tell you that, not to put Starlinks on the spot, but ever since the Starlinks got on orbit, the number of conjunctions has almost doubled. So what I'm telling you is that conjunctions don't equal collisions, but they do mean that things are crisscrossing each other. It is an increase in traffic patterns. Here you can see the relative speeds spiking at about 15 kilometers per second. You have some low relative velocity encounters, even rendezvous right here on the bottom. This is like space station things at the space station. Here you can see the altitudes. Before the Starlinks, this was a spike at about 800 or so kilometers. Now you see this spike is pretty much dominated by the Starlinks, and that's just going to increase. Again, not saying that it's bad, just showing you kind of what the current traffic patterns sort of look like. And so these are things that we just need to be aware of. It's not meant to be alarmist. Again, conjunctions don't equal collisions. Conjunctions could lead to, could be collisions. And so we just need to be aware of these things. And I guess another thing to kind of just say here before I get off the stage is, when I talked about orbital highways, what do I kind of mean? So here on the left is a plot, a snapshot of about 4,000 objects in an astrograph, where the color is the orbital inclination of these objects. So this is in Cartesian Euclidean space, as it were. And so, has what you know as kind of 3D space. And then we took the same objects and basically computed their specific orbital angular momentum. So it's just the position crossed with the velocity vector. So h is r cross v for those that want to geek out a little bit. And we haven't changed the color coding. This is the orbital inclination. What I'm telling you is that in this space, you can naturally see these clusters. So here on the bottom are low Earth orbit. Here on the top is geo. In the middle is like geo transfer orbits. And so what I'm telling you is that we don't have objects uniformly populating orbit. We put things on a specific orbital highways to serve specific purposes. These highways are finite. Okay, we don't. Mother Nature grants that. The curvature of space-time provides that. There isn't a second one. So we need to protect these things if we want to be able to use that for humanity's best purposes. And so with that, I am going to call it good. And thank you very much.
Oh, thank you, Mariba. That's brilliant. What a start. I mean, some thoughts there. I mean, I know that the general lifetime of once a defunct object or something that was in use, we've still got this 25-year type period in place. Yet, am I not right in saying the new world of LEO, aren't we looking at replacement cycles of objects in, say, 5, maybe 10, but let's say 5 years? And therefore, if they're still, shall we call it, not controlled in any way, not even sure some of these objects have even got propulsion to move them. So how do you get rid of them so you can make space to replace them? I mean, has that ever been thought about, or is it just going to let nature take its course? And does Mr. Kessler crop up in all this scenario eventually? I mean, what do you think?
Yeah, so I'll say this, right, and I'm certainly looking forward to seeing what Jonas and whatnot has to say as well. But my opinion is this: I try to focus less on Kessler and more on this carrying capacity. And the thing is, the carrying capacity is a real thing, and it can get saturated. And I would say pragmatically, if somebody were to say, okay, you're using words, jargon, what does that like mean in real terms? I would say that the carrying capacity is exceeded for a given orbital neighborhood when our decisions and our actions can no longer prevent loss, disruption, or degradation of space activities and services past some threshold, like per year. Like if 10% of our actions can't prevent loss, disruption, or degradation, like per month or per year, some agreed to threshold, then we should say the carrying capacity for our purposes has been exceeded. That is something quantifiable. That's like a real thing. And so I think that is what needs to be used as the metric to help regulate when we need to get rid of stuff. Yeah, people are putting things in lower Earth orbits, and they're just saying, I don't have to worry because Mother Nature provides this natural cleansing mechanism, and it's going to rid the system. It's a natural death rate of anthropogenic space objects, right? The thing is that if everybody hangs on to the 25-year thing, the 25-year thing didn't take into account that there'd be tens of thousands of these objects slowly decaying based on whatever Mother Nature imposes on these. And so that's the thing that needs to get reevaluated. I would say we need to actually develop something like, let me call it a space domain digital twin, a virtual replica of the domain, to play all these things out with each other, because it's a complex system. And interestingly, the decisions that certain agents make is going to be dependent on the decisions that agents made before. And the thing is, we have no idea. We don't know all the decision-making criteria of all the participants in that same domain. So it's very much unknown. I'm actually quite, I'm scared. I'm scared because our actions are outpacing regulation, and we have no idea what the unintended consequences are, but people have the licenses to just launch and just do it, So it's very scary to me.
Well, thank you. And I mean, I have to say for my group, the SATCOMS Innovation Group, as we were, our mission is to still deal with good old interference in spectrum, radio frequencies, for those out there that are listening. And we've often said the ITU has no model even for spectrum, just spectrum, which is, can't crash into each other. We can make it useless by jamming each other up, but we can't crash into anything. It doesn't damage the physical sense, but it makes things useless. We don't even have a model that you can add all the different things being used into the model and add the next layer of different things. And I must admit, I think it was some years ago, and I think it was when we first met, we started to talk about, is there any common model? Could we start with the model of today, which of course is now worse? So we haven't got the first model of just those few, and I call them the few now, the geo arc in the geostationary arc, which are the few. Yet we have to protect all, like you say. So I agree with you. I'm scared too. That's the point of this seminar. You know, plastic is scary. Well, debris in space is equally scary, if not, I don't know, worse. I think they're both equal. I think it's an equal one. So, well, thank you, Mariba. That's a great start. So now we're all scared. Jonas, now I know, you know, we move on now. And I mean, Mariba's sort of led us into this. We've seen some of the stuff you're probably getting into. I mean, we're sort of starting this SSA, space situational awareness. What a mouthful that is for everybody listening. Well, yeah, how are we aware? How do we monitor? How do we get those 4 different predictions on one satellite to be one prediction? I know, Valentine, if you're listening there, I could see your thing smiling. You know, there's a lot of data and stuff. But Jonas, I know you're looking at tracking objects, how to monitor. This is the part that everybody has to do. I don't think it can be down to one, but lots of people, and you've been involved with DLR, our friends at DLR. So Jonas, take us into the realm of how do we get Mariba to be a happier bunny with knowing where a satellite really is, rather than thinking I've got 4 thoughts. So Jonas, over to you.
Okay, yes, Martin, first, thank you very much for the introduction, and I'm also very happy to be part of this panel today. I actually hope that I can light some shed into the question you asked. We will see this. To give a bit on my background, in my first life as someone who's endeavoring space, so to say, I was working at the Institute of Space Systems at TU Braunschweig. And at this institute, I was basically researching on exactly the topics that Mariba just mentioned. So looking at how is the space debris environment evolving over time, and how can we measure capacity, how much room is left up there, and how can we avoid that space gets too crowded, and then how to explain this as simple as possible to make the decision, or to bring the decision makers in the position to put up rules to act on this. I don't know how successful this was, but I'm really happy that the overall discussion moved away a little bit of doing only long-term simulation and showing increasing lines, but actually looking into the part that you define how much space do we actually have, and not saying we have an increasing number of objects, because just the number of objects in all space is not what's relevant, but where they are and how they interact. And yes, after this time at the Institute, or already during the time at the Institute, some colleagues of mine and myself noticed that we've developed a lot of tools and ideas and approaches that maybe is not the full solution to everything that's going on in space, but it's definitely something that can make sustainable spaceflight easier for partners and people who are involved. And yes, today I would like to give you a short introduction into how this whole thing we call SSA works, and what our approach is to contribute to people acting more responsible in space. And for this, I would do this a little bit more classically. I prepared some slides and I would go through them and yeah, explain what we're doing. So yes, so me and my colleagues, we founded a company It's called Okapi orbits. Some of you maybe got around them already. And yeah, our approach is really making space and space traffic management easier by providing this as a service. And don't be, just so you know, I'm not going to talk too much about our company today. I'm more trying to go a bit in the concepts, what we're actually trying to solve. And I always like starting with this image because actually, even when you're talking to people who are quite evolved into space, many of them are surprised about what's actually going on there. So you can even talk to people who've launched maybe 10, 12 satellites. If you tell them space is crowded, they're quite surprised. So I always like starting with this, that since mankind started the endeavor looking at space, we've done with all things that we endeavor as humans, we're leaving our things behind. And I'm not going too deep in the numbers here, but just to put some figures to bring up perspective, as of today, we have about 900,000 objects in orbit, larger than 1 centimeter, that are brought there by humans. And the smaller they get, the more you have. And these objects move with with velocity of up to 7.6 kilometers per second. So even the very small ones make them very dangerous, so to say. Distances from Earth between the 300 and 40,000 kilometers. And we want to analyze what's going on in space. And for this, we require knowledge of the objects in terms of characteristics. So how do these objects look like? Because this is important to describe how they behave and how they move. We need to know where are they and how fast are they at this point, so we can extrapolate their movement into the future. And I think this point was made very clear by Muriba. We also need to understand the behavior, because with everything we observe, we always can only say where it is at the moment, but we cannot say where it will be in a certain time from now. We only can make predictions that come with uncertainties, and if somebody does a maneuver in between, our prediction is completely wrong. So actually every image we have of space is already outdated at the time that we get the image. And now I would like to go a little bit, it's not too much technical detail, but a little bit into how actually we derive this image that we have, and some ways forward how I think we can improve on this. So what's known at the moment? So I told you we know about 900,000 objects are supposed to be there. These are from modelings and simulations, and really known by measurements. We know about, or we have known so far about 50,000. Half about them have decayed, and the other half is in orbit. This is our knowledge. It's objects from about 10 centimeters and larger. And of these, only 12.5% are really satellites that are still active and that are used. So for these, there's usually even a better knowledge than for all the rest. And for everything that's out there that's not part of these active satellite, you can say this is the space debris or space junk or orbital debris, or however you want to say this. And on the side, you have a short statistics, how this is distributed, but I won't go into detail of this here. So when we now go further, how do we know these objects that I just mentioned? There we have to look a little bit on where are these objects located, and also be working very simply. You can say there are 3 regions in space that are used for space activities by mankind. The first one are orbits in low Earth orbits. These are roughly about up to 2,000 kilometers. In there, we have regions that are used very, very much. It was also shown by Muriba. These are especially sun-synchronous orbits, for example, where we have very good conditions for Earth observation. And in here, we have a lot of Earth observation missions, missions that monitor Earth for weather predictions. And now, since or starting basically last year, a lot of communication satellites for large constellations that are going up. Then we have the second important region. It's the geostationary orbit. This is quite well known because everybody who has used satellite television in the last had one pointed an antenna on a geostationary satellite. So this is the reason why these orbits are very famous, because you position one satellite there and it always, more or less always, stays on the position where you've put it relative to Earth. So this is the second really important region where we have a lot of going on. And then in between, there's something that's often forgotten about when talking about debris. We have the so-called medium Earth orbit, and in altitudes of about 20,000 kilometers, we have basically all the navigation constellations. So there are GPS satellites, Galileo satellites, Baidu and GLONASS satellites. So they are mostly there. And depending on where these objects are, we use different kinds of measures to observe them. So when we look into very high altitudes, it usually makes sense to use telescope. They use reflected sunlight, and they measure the directions from where we saw a spot of light, basically. And from this spot of light, you can make an assumption about an orbit that an object would have been. They need quite long observation time usually. And there's one distinct disadvantage: objects have to be in sunlight. So this doesn't work very well in low Earth orbits, because there you have only very short times over a day where you can really observe these objects. Then when we get closer to Earth, it makes much more sense to use radars, that you have an active signal. So instead of using the sun, you send your signal yourself. With them, you can measure direction and distance. So you have more information in one measurement compared to telescopes. And they have the advantage to work basically during all conditions. So if there's a cloud, it works. You don't have to wait until it's dark or your object is sunlit. It always works. But they have the downside that they require an active signal. And so they are only applicable for close objects, because the further they get you get away, the more energy you would have to put into the system. And so these are the basic foundations of how objects are measured, with their advantages and disadvantages. And there are some other measurements that are getting used as well. Just to note them, so you can, for example, use telescope and measure the infrared spectrum of satellites to describe their characteristics. So you can see hot spots at the satellite and make assumption what's going on there. For our active satellites, you can use RF tracking. So you can basically sniff when somebody is communicating with their satellite and tell quite precise the position of them. And you can also use it to make assumptions about whom they're talking to, what is their intent, what are they doing, are they active, is there anything wrong on the satellite? So it brings a lot of additional information. And there's one thing where you mentioned it, Martin, in the introduction, where I did some research some time ago to use combined active and passive measurement, combined active and passive measurements, so-called laser ranging, where you would do an observation of an object first, usually with a telescope, to find roughly in which direction you have to look, and then point a laser on the object. And this is one advantage of being able to give a very precise measurement, because with a laser you can very precisely, due to a small wavelength, determine the distance to an object. And when you have a very precise distance, you basically have less uncertainties in your measurements as when you compare it to a telescope, for example, where you only know the directions. So these all together can then be used to set up a database of objects that we then further can use to analyze it. And I don't want to go into too much detail how this works, but just to show you that it's basically, it's a complex process to process measurement to having a satellite catalog. And what's important in this process is that at every step, so the blue steps are basically in this image are a processing step, and the red ones are those where we have some kind of data collection. And in every step, we include assumptions and uncertainties. And all this leads to the issue that Moriba showed in the beginning, that even if you use identical parts in some areas of this process, if it's different in others, you will always get a different result, and it's really hard to say which of these results is correct. And this is where we at Okapi Orbits actually have a somewhat similar approach as Moriba, that we try to use as many different sources as possible to get to an image that we can then process further to provide actionable results to users of our system. So this is the big but. Basically, having the data is one thing, but then using the data is a completely other thing. So once processed, I said this in the beginning, the observation data is always already outdated. So we need to have additional information that helps us saying what will this object be doing. One thing that can help is if satellite operators, for example, say, we are going to do a maneuver tomorrow, please consider this, and then it can be considered. Other approaches are looking into behavioral analysis to predict based on a mission profile what could be an action that the satellite might be doing tomorrow or within a week. But there, of course, you again have large uncertainties. Then we always have things to the data attached that we can only describe stochastically, because we have these uncertainties that come directly from the measurements. We have then some uncertainties that come from the modeling, so different assumptions for in the physics. There are always uncertainties from processing and so forth. Then we always only know what's in the catalog and we don't know what's not there. So currently I showed you we know about 25,000 objects, but we know that there should be 900,000 up there which are dangerous. So there's still a big gap. And then we have the problem that the data from different entities is usually highly fragmented. So if someone wants to pursue SSA, so to say, they first have to start getting all this data and somehow combining it so it can be used together. And with the issue of all these different assumptions and models that were involved to create the data, you can understand probably that overall it's quite complicated. And yeah, maybe just very short, this goes now in the direction what we are doing. We also basically, the approach of Okapi Orbits is to gather as much as descriptions of what's going on in space together. So this includes catalogs that are out there. This might include specific tracking data. This includes data that's available from satellite operators themselves. Can also be already available collision warnings, and then put it into our platform where we do a lot of data processing initially and a lot of astrodynamic calculations. And what we're also looking at is using, I call it artificial intelligence, because it's actually, there are many different methods that come from very many different realms that help us to basically decide which data is most appropriate in which situation. That helps us decide what data can I trust under what circumstances, and then helps us decide what action we should take in an unclear situation, such, for example, a conjunction. This is all still a learning process. We're not at the point that we can say we have perfect solutions here, but this is basically our approach that we are taking to make space situational awareness easier. And then as we're a commercial business, we have customers, and our idea is basically to provide our customers with measures that they can use without even noticing this. So we are striving for a very deep integration of, for example, collision avoidance for satellite operators into their operations. So their operations are safe, but they don't have to do this by themselves. It's basically working fully automatically, and it's considering the actual tasks of the mission. And yes, this is, I think, the most important point I wanted to highlight. And from there, there's always the question, okay, where are we now and where we need to go? So from my point of view, these items currently very important. So we are at the moment in the age of space situational awareness. And the name already says it's a very passive thing. So we know something is happening, but we don't steer this, we don't act on this. So the next step, from my point of view, is really going towards space traffic management, which is something active. So we steer into a direction where we want to go. This has been around quite long now, but I think slowly we are progressing in better directions to get to this point that we can say we're doing space traffic management, even though there are a lot of things still to be done. And to get there, we think that this basically requires much more real-time coordination between all involved space actors. Currently, more or less everybody is doing what they want. And this requires two, or at least two, I think there are many more, but two in the minimum. First, more openness and transparency to share intents and plans. And this is interesting. We talk a lot with satellite operators, for example, and you can say it's 50-50. Some treat their orbit as really secret, and others say, yeah, sure, you can share it. So it's in the internet anyways. And what we also think we require more legal frameworks. They can be actually legal. They can also be other dimensions that define really clear rules for in-orbit behavior and also make space actors accountable to their actions. So currently you have to, in some parts, prove beforehand that you intend to behave well, but if you don't, not much happens. So, yes. This was my main message. Thank you.
So thank you, Jonas. And as we said, data sharing. Well, there's an important point. So we've got a short video from Astroscale via a friend and colleague, Harriet Brettel. And she's going to look at addressing the challenges, trying to clean this place up, i.e. take some of those objects away. How on earth do we do that? So I'm going to hand it over to Harriet and let her explain what Astroscale's thoughts are on the subject of debris and where they are trying to make that next leap of faith from the data that Jonas collects, from the thoughts that Mariba's had, to what Astroscale are kind of do in practice. So thank you, Harriet. Over to you.
Hello everyone, my name is Harriet Brettel. I'm the head of business analysis at Astroscale, and I'm here today to talk about addressing the challenge of space debris. So there's three things that I want you to take away from this presentation. The first is that we rely on satellites in everyday life. The second is that space is getting crowded. And the third is that we need to act now to ensure future space sustainability. Okay, so going back to that first point, our daily lives rely on space technology in a whole host of ways that you might not expect. We use satellite information to support traffic management, weather forecasting, broadcasting with your satellite TV. We also use it for disaster management, so looking down at the Earth from space to be able to understand what is happening on the ground right now and what can be happening in the future, whether it's weather forecasting or understanding climate change. We use satellites to help us to get from A to B with navigation and logistics. And also satellite technology enables us to associate timestamps that are used for financing and international trades across the global banking system. This is an image of what the space environment looks like when we're only considering the active satellites in orbit around the Earth. So these dots aren't to scale, but each one of them represents an active satellite that is providing some of those services to us here on Earth. We've got two different regimes that satellites occupy in space. So while space is really big, there are finite regions in which those satellites tend to live. The first is what we call low Earth orbit. These are the satellites that are operating really close to the Earth, so anything from 300 kilometers above your head to 2,000 kilometers. And they're traditionally providing those Earth observation services, looking down on the ground to see and understand our planet better. Further out, we've got the geostationary Earth orbit, or GEO, and this is typically where telecommunications satellites sit. The reason for that is the far out distance that they are, 35,000 kilometers, give or take. They rotate around the Earth at the same speed that the Earth rotates. And so that means if you're looking out at a particular point in the sky, the satellite will remain in a fixed position, which is really useful for communications. So as I said before, each of these green dots represents an active satellite. But if we consider the space junk that's orbiting around the Earth as well, with each of these orange dots, we can see that the Earth's orbital environment is becoming congested with increasing amounts of space debris. And in fact, over 95% of the objects in orbit are pieces of debris. So less than 5% of the artificial objects larger than 10 centimeters in size, are used for satellites providing those services. Everything else is posing a threat to those satellite services that we rely on in everyday life. And so here is what the Earth's orbit looked like in terms of artificial objects in 1957. And here's what it looks like a few years ago in 2018. So obviously this is just an illustration, but you can see there's a huge amount of additional objects orbiting the Earth. And again, the vast majority of these are pieces of space junk. So what we're finding is over time, as we launch more and more satellites into orbit, that means that we end up with more and more debris if we don't do something about it, which in turn increases the collision risk for those operational satellites that we rely on, which ultimately leads us to an unsustainable orbit. And this challenge that we're facing in the Earth's orbital environments are not too dissimilar to the challenges that we face on Earth, whether it's climate change or plastic in the oceans. Everywhere humans go, we tend to leave waste behind. And so what we're looking at doing in space is trying to learn from the lessons of Earth and incentivize satellite operators and others to take environmental issues seriously and to clean up after themselves once those satellites are no longer providing value. Okay, at this point I'm going to introduce Astroscale. So Astroscale is a company, we are the space sweepers. Essentially we are all dedicated to a mission of securing orbital sustainability for the benefit of future generations. We were founded in 2013 and we now have over 100 employees in 5 offices around the globe. Our headquarters are in Japan, but we also have offices in the UK, the US, Israel and Singapore. We're a commercial startup that has raised over $191 million to date, and this is all to help us with our mission of protecting the orbital environment and keeping space clean. So we're actively addressing this orbital debris problem that I've introduced to you in a number of different ways. This is a really challenging problem to solve, and it's going to require us all working together to tackle different aspects of it. So we're looking at developing technology that can do something about the debris problem by removing failed satellites and pieces of debris from orbit. We're working to identify the business case and the commercial incentives to help satellite operators be incentivized to use the technology that we're creating to address this problem. And we're also informing international and domestic policies because, as we said before, this is an environmental challenge. These are going to require coordination and collaboration from actors all around the world. At Astroscale, we're looking at developing 2 kinds of debris removal service. The first is what we call the end-of-life service, where we're looking at mitigating future debris. So here we're looking at preparing satellites that are about to launch in the future and making sure that they don't create any debris going forward if they fail or unexpectedly run out of fuel, which means that they potentially run the risk of being future pieces of debris. The second service that we're looking at developing is what we call active debris removal. So this is addressing what we call legacy debris, pieces of debris, whether it's large failed satellites or stages of rockets that remain on orbit, to remove those existing high-risk objects from orbit. And here we're looking at working with space agencies and governments to address what is fundamentally an environmental problem. So let me talk a little bit about the ELSA-D mission, because this is really exciting. So ELSA-D is going to be the world's first end-to-end debris removal demonstration. You've got a picture of it here on the screen. So what you can see is two spacecraft. We're going to be launching these both at the same time. And the gold-colored spacecraft, that's ELSA-D, that's our demonstration satellite. And the gray box on the right is our client satellite. And we're going to be demonstrating in a number of different scenarios that our servicer ELSA can successfully find, rendezvous and capture the client satellite under a number of increasingly challenging scenarios. And so what we're going to be able to demonstrate here is our capture technology. So what we're looking for with the future end-of-life service is getting satellites to include a docking plate on their satellite before they launch, which means that our ELSA servicer is able to go up and remove them safely from orbit if and when they unexpectedly fail and need this kind of service. The second mission that I wanted to talk to you a bit about, which again is really exciting, is the Address-J mission. So here what we're looking at doing is active debris removal of environmentally critical objects. So Astroscale is working with the Japanese Space Agency on the first phase of the CRD-2 mission. And the first phase of this is going to be to go up and inspect a piece of Japanese space debris. And the second phase that is planned for 2025 would ultimately would be to go and remove that piece of debris from orbit. So what we're looking at here is a number of really exciting missions in the next few years to demonstrate the technology to be able to address the debris problem that we face on orbit in a way that allows us to keep space clean and usable for future generations. So just to remind you of what we said at the beginning, those three key takeaways. The first is that we rely on satellites in everyday life. The second is that space is getting crowded. And finally, we need to act now to ensure the future of space sustainability. That's exactly what we're doing at Astroscale. I hope you've enjoyed this presentation. Please visit our website if you have any more questions or want to learn more about what we're doing. But thank you so much for your time, and I hope you have a great rest of your day. Thank you.
Thank you, Harriet, for that insight. That was brilliant. And it shows that we probably can do something practical up there. But, you know, I'm going to get to my next guest now, because Valentin and I have had a little chat about this, and we had an interesting title for his part of this: to fix or not to fix. It was more to do with probably can we fix is more the bigger question, because I'm sure we can take some of the debris away, and hopefully the very big objects, as Harriet just explained. But, you know, at the end of the day, like Jonas said, we've got lots of dangerous objects from 1 centimetre. How on earth are we going to hoover that lot up? I mean, this is a real problem, and it's a now problem, not a tomorrow problem. You know, this is where we are now. If anything, tomorrow might be worse. Who knows? Well, we're predicting it probably will. As each day goes by, things will happen. How many small objects are crashing into each other and creating more small objects? I'm sure this is not a pleasant game, and I'm not sure we've got any right answers. So, Valentin, without further ado, I'll hand over to you to take us into the last part of this wonderful puzzle of debris.
Very much, Martin. I'm Valentin Eder. I'm living in Vienna, having here our company Space Analysis, and yeah, we are doing big data analysis, maybe mainly for the operation support for spacecraft operation. And yeah, my background is not so clear, straightforward. I did had couple of lives before I entered into space, and small companies, big companies, and since 7 years now, I'm running my own company called Space Analysis. And my background is industrial background. I call that in this way, industrial background. Then it is power supply, high voltage power supply. And then I came into the space and payload operation monitoring. And since 2 years, with a colleague of mine, we entered the stuff of space debris, and my non-knowledge made me curious to say, what's going on there? Yeah, and I tried really to find out what is going on there, and until now I do not have a real clear picture. Thank you, Moriba, and thank you, Jonas, for your presentations. I'm approaching the stuff from a little other point of view. Okay, what are the applications? Just that is a quick reminder from my side what we are doing with the space stuff. So it's navigation, everything what moves, artificial and natural things, everything what have relation with location, can be even construction, roads, rails, whatsoever, and everything what have correlation with time. Can be, for instance, the mobile phone networks, time synchronization for their, that they're working well, stock exchange trading, any measurements what they are doing, even RF location, RF emitter location use, GPS stuff. That's navigation, and that's a location-based service and time service. Then everybody knows human space flights to moon, the Artemis program, China's activities, yeah, Earth observation, weather, sea, land, climate, geologic, disaster management, and very important also intelligence is up there. Then exploration, yeah, Mars, Moon, Rosetta, Sun activity, Venus, Mercury, we learn a lot of that out there. Astronomy, separate thing, and then again, telecommunication, what is the major part, what's going up there. Coming back to that later. And then there are services, down, up, middle stream, and now coming to debris measurement and removal, what Jonas is doing. And then there is something new coming up, mining. No idea what's coming up there. So that, keep in your mind, that's what we are, let's say, the human being, are now have benefits from that. Now coming to this curve, what Moriba told, the so-called birth rate and death rate, I call that dynamic, good. Here you see the increase of objects, good. And here you see that so-called death, that what removed from the catalog. So the scale of this is the scale of this. And here you see, okay, RF means payload fragmentation debris. Okay, the RF, here happens something with a satellite, good. And here the yellow one are satellite debris, not any of collisions. So that's just to give you an idea. That's the so-called COVID curve for space. We are in the exponential curve up now. Yeah, here are the new infections. Here are the healed ones. So who is now active there? Owner and usage. You see here clearly. Here now coming back to the number from Jonas, about 2,800 satellites, active satellites, operating satellites, okay? Mainly are communications, Earth observation, and then here you see technology development, okay? And here a small part navigation. Mainly commercial. Quite interesting, government and military. So if you just see commercial and you put this up to here, you see that is the main part of everything. So now you have a feeling, you should have a feeling, who is now the game player there? And here you see, Leo is, this is communication satellites. Here is a part SpaceX, for instance. The same picture, just in 3D. Here you see the numbers, the counts. We have here commercial, government, military, civil communication. Not so much. Earth observation, commercial, quite interesting. Good. Technology development, everybody's doing roughly the same. Military and navigation, good. And then, of course, space and science observation. The rest is not really relevant. Now, how about end of lifetime? I'm coming back again to the number from Jonas, 2787. Good. And now I had a deeper look into this data, and I noticed that out of this number, 478 or 17% are out or after end of lifetime, meaning they are called operating satellites, but they are not operating satellites. In that sense, it might be, it might not be, nobody knows, or we don't know, public unknown. And out of this 17% so-called operating out in this catalog, it's called, if I'm looking to now, this one, blue is Leo, red is MEO, and that is the geo part. If I'm looking here now just to this one, and we know from Jonas, that is navigation systems. Here we have quite an interesting number of satellites what are out there calling operating, but definitely are not. And if I'm looking to this 400 satellites, in Leo, there are so many governmental satellites what are not anymore, what are, let's say, quite sure out of not anymore mobility. So if they can't move out of the way. And here you say in the commercial part, in geo, these are all the old television satellites in the number. Here I just had made some ideas of how much material that is in mass, in tons. So about 350 tons commercial stuff, about 200 tons governmental, and commercial and military stuff is the same amount, but you see in different orbits. So the thing is, what I want to tell you here now, coming to the point, is that data, even if there is something written, you have to look really into clearly get a validation or a correlation or somehow feeling can that be true or not? Similar like Moriba said, where is the satellite? And I have here an example, we even don't know what is the satellite. And here also a small point is, if it's a so-called operating satellite, and meaning operating is what? Is payload operation? Fair enough, good. That's an operating satellite. But if the payload breaks and the satellite itself works, is it an operating satellite? Is it not an operating satellite? So for me, the classification what we have today in the satellite catalogs, where I can say I have rocket bodies, I have payloads, and I have debris, does not help me in space traffic management, because I don't know if they are movable or not, if they have active propulsion or not. They can move out of the way. That's an what's quite an interesting stuff. So where space debris comes from? We are all, let's say, focused on the stuff collision. For the moment, in the last 10 years, only less than 1% of the space debris comes from collision. The main thing is, if I just come here, it's propulsion, it's unknown, and it's anomalies. Good? We are more than 3/4 done, meaning the danger to get a space debris for the moment, that's until now, is the spacecraft itself. Meaning the safety, we showed something up, we've launched things up, and the satellite itself is not, let's say, safe enough or secure enough that it does not spread, it does not get defragmented. So, when does defragmentation happen and how long is the incubation period? Here you see that is years from 0 to 60, and here are different classification of defragmentations. And you say, okay, this is the classification. Here you see propulsion, then upper stage problems, motor problems. And if I'm just looking to between 0 and 10, the size of the bubbles show me the number of defragmentations, parts, number of parts. You see, between 0 and 10 years is the major problem of defragmentation of the satellites. And then between 10 and 20. So you can say, okay, somewhere between 10 and 12 years, somewhere is the dangerous part. It's the so-called infection, okay? And then the next step is I'm coming to when now it comes to a conclusion, collision, sorry. It comes to a collision. Meaning, first I get debris, and then it might come to a collision, and then we have again 10 to 20 years. So if I say, fly up now a satellite, it might become or make a defragmentation, and then again 10 years later, meaning today we have 2020 still, and that means in 2040, it is most probably the most dangerous time for all the SpaceX satellites. Yeah, what about last week? Here you see counts. We did similar to Jonas. We are calculating the conjunctions, so the meetings of the parts, and we did some statistics, easy statistics, where we say, okay, number of counts of conjunctions, not collision, conjunctions, within 1 kilometer, within 2 kilometers, and within 3 kilometers. And if I just look this 1 kilometer, I have about 600 counts every day coming close to each other. And in this week, I had 1 in geo. If I now expand that to 2 kilometers, I'm not 600, I come to 2,500. And if I'm coming now to 3 kilometers, I'm coming to 5,500. If I'm just taking this 660 events, good? That means average pause between close flyby events is 2 minutes and 10 seconds. Meaning, it's quite a big area out there, but every 2 minutes, roughly, 2 parts are coming so close together that we don't know if they have a collision or not. And the point is, having now an uncertainty. I personally, I don't know if the dangers, if I say, how good is the data of the TLLs, two-line elements, is 1 kilometer. Are they good enough for 1 kilometer? Are they good enough for 2 kilometers or 3? And then we can say, aha, how now is the so-called carrier capacity from Moriba? Can we say, is this a carrier capacity to have every minute or every 2 minutes? If I'm looking now to the straight stuff, I say, merely an accident, where I say they are coming so close together, but we don't know if they crash or not. Could be an idea of carrying capacity. And cleaning space, that is just my personal point of view without, let's say, stating the others. It's not realistic with a significant impact to risk reduction. Where if I'm just dreaming to say, okay, we start to clean space, where we are starting at the most risky areas. Of course, we should do that, but how we then are we really gonna be there? Where are the parts? We have the problem of now Moriba, and we don't know how to catch them. There is ENVISAT. It's a 18-meter long. I call that a bus, and a bus having a 3-axis rotation by about 20 seconds. Unbelievable. How to catch that? Yeah. And if you have catched it, what to do with that? So for me, cleaning is not realistic. What should be done is remove of the some of the big things. ENVISAT is a serious problem, and all the rocket bodies. Rocket bodies is exactly these course, what you say. As long as we are in the same orbit, it's not a big problem. But coming back to the nice picture from Moriba, where I say, aha, we have clusters. These rocket bodies are exactly the cross-cluster stuff. Yeah, what if we switch off the light? Wikipedia writes, there is not a physical impassable barrier. That's right. But I would say we add economic barrier, safety barrier, and risk barrier. Economic barrier means you don't easily to say nobody will get, you don't get an insurance for your stuff. And are you really sure that you fly up a satellite without an insurance? Safety barrier, if you are up there, how safe it is to be there. Good. And risky barrier is, okay, now you're bringing up new stuff there. You increase with your new satellite, with your new object, the risk. So it's a mixture of barriers. So it might come to the situation like in the COVID that we are not all dying, but at one point we get to a lockdown. And that is a kind of lockdown from the Kessler syndrome. And if we are locked down, we have the problem that we will not get any new satellites up there, and the existing ones running into end of lifetime. And end of lifetime means that they are dying up there. There will be debris. Okay, fair enough. What we lose? OECD made an interesting study, of the economics of the impact of space debris, and out of this, loss of lives, science and so on, what we add and what we see as the most important, biggest impact to all of us is location-based service and time service are disrupted. Good. meaning autonomous driving cars are obsolete. Significant reduction of air traffic and ship traffic, offshore and onshore. What means ship traffic without the GPS might be problems. You have to get too old stuff back, yeah? And air, clear, all what is offshore, transatlantic, you have to have a big distance between what reduces now again the carrying capacity. Yeah, what also is location-based service, modern military operation. And international high-speed trading is affected, because if I now order in New York something what is traded in Tokyo, fair enough. It have all the world have the same timestamp, and that is, let's say, that enables a lot of also business stuff and anytime synchronization. Satellite broadcast, information flow is disrupted. I call that now daily broadcast from home, meaning, okay, we have BBC here in Austria, is same as we have Turkish TV, and we can also watch South African TV here in Austria. This is then history. And yeah, emergency and diplomatic communication just would be interesting for me how then they will go to communicate again. And if satellite broadcast and data flow is away, remote war is obsolete. So anything what means, we will fly a drone from here to there and do something, this is obsolete. Earth observation, yeah, intelligence is significantly affected and disaster management is affected. So that is, if the light is off, time would change. Yeah, that was it from my side. Yeah, back to Martin.
Well, thank you, Valentin. Question, I noticed in the stats, you were thinking that if you roughly look 12 years hence, that's roughly when trouble starts with your fleet possibly colliding with something else. You were looking at that 10 to 20 year period, and it looked to me around, you were saying about the 12-year period. Surely that possibility must draw closer. In other words, the 12 years must reduce as we put more, especially in the LEO orbits, where we are really filling them up. And when we're not talking 2,000 or 3,000, we are talking another 40,000 commercial satellites, and in the next 5 years. I mean, I know the business cases. I'm not going to worry about people's business cases. That's their problem. But, you know, Starlink is already putting, what is it? There's a number up there already. It's quite large, bigger than we've ever seen before, and it's just above our heads. Am I right? Are we looking at getting worse? It's not going to get better. Are we going towards reducing that 12-year thinking into, say, a 5-year thinking?
In the collision stuff, you know,
yes.
There is two things. First of all, the industrialization itself, meaning where the space debris is coming from. If I'm now reduce the, if I'm now say industrialization, does that mean also that the quality of the satellite will increase due to standardization and industrialization, or does that just mean produce something to best effort? And until now, I'm just what my knowledge is the approach from the big satellites is just get it cheap and make it to the best effort. So minimum viable product approach. What does mean that the danger of space debris will definitely get very much higher. That's the first stage. So meaning that the risk of defragmentation will increase with the industrialization for the moment, as my knowledge is, because it's not a quality standard, it's a price standard, what they are looking for. And the second thing is, of course, the number. So I increase two things. First of all, I increase the uncertainty of the quality, and then I increase the number. So it's a double exponential function.
So on that note, I will now stop this session. Thank you everybody for listening. Thank you again to those that helped us put all this great input together, and look forward to having a bit of Q&A with you all in about 20 minutes. Thank you.
Well, thank you, Martin. What a mess.
Sorry about that. I did say it wasn't entirely a happy story, but you can tell from the panelists that they do know their stuff, and I have to say, with the people we know and those that have been on our panel especially, it's nice to know we're in good hands. Over to you.
In the Hitchhiker's Guide, Douglas Adams said space is big, but we're paying the price now, I guess, for being a rather complacent throwaway nation, where we've just relied on it being big. But problem is, the access to space is through our very narrow atmosphere, which isn't as big as the rest of the cosmos. So yes, it's a challenge, and I do hope, with the brains that we've got on the panel, obviously it's a very serious problem that's being very seriously addressed, and I look forward to tracking what's happening.
And now for something completely different. I'd like to focus on the presentation of the EMSTA Award to this year's Arkwright Scholar. This award is made in the form of a cash award and a framed certificate. And each year, the Arkwright Foundation send us a short list of candidate portfolios with CVs and recommendations from their schools. This year, we received details of 4 outstanding candidates, and it was a really tough task. But after a lot of deliberation, we separated out a winner. But again, COVID prevents us making the presentation live and in person. So I am delighted to invite Amanda Atfield, the Head of Design and Technology at the Berkhamsted School, to make the presentation on our behalf. Thank you very much, Amanda, and over to you.
This is the EMSTA Scholars Innovation Award. EMSTA is delighted to present an annual award to celebrate the achievements of young people interested in science and engineering. The award takes the form of a cheque for £150 and a very nice framed certificate, as you can see here. And that is presented to an outstanding Arkwright scholar for this particular region. The Arkwright Trust is a charity which aims to promote engineering to young people and has several hundred scholars each year across the whole country, although this year they were reduced in number to less than 300, so this is a very prestigious accolade. In 2019, the award went to Lucius Wong of the Knights Templar School, Baldock. This year, the award goes to Dominic Coles-Saferio of the Berkhamsted School. My name is Amanda Atfield and I'm Head of D&T at Berkhamsted. Today, I've been asked to make the presentation of the EMSTA award on behalf of the EMSTA themselves because of COVID-19 restrictions. It gives me huge pleasure to present this award to Dominic, as in my 16 years of teaching, I have never seen such a naturally gifted and talented individual with such a passion for engineering. And he is as creative as he is technically proficient. Dominic was inspired by his grandfather, a civil engineer who travelled around the world completing civil projects. Dominic is clearly self-motivated, as he has been taking a MOOC course called The Art of Structural Engineering Bridges from Princeton University, and plans to take another MOOC course about general structural engineering to further his understanding and interest in building structures, and that's alongside his Year 12 studies. He was nominated to participate in a sustainability conference with a design engineering consultancy to discuss the proposed design for our school's new sixth form. He was able to talk to industry professionals and share his input on how to make the structure more sustainable, and he really did contribute to that discussion. That gave him great insight into how the design process works and the importance of collaborating with people with a diverse range of specialisms to achieve a common goal. Dominic would like to go to the Bartlett School of Architecture and do an undergraduate course in engineering and architectural design and complete a postgraduate course in architectural design. So he really has his path mapped out for him. Dominic has always been interested in architecture, from what I gather, and the structural and material elements of it. And he's very passionate about the rail industry as well. So would like to incorporate these two together. He wants to be an engineer to help design infrastructure in developing countries, which is to his credit, especially in the major urban areas, and to reduce congestion by creating railway links between major cities and countries in order to create sustainable development, which is a real passion of his. EMSTA are delighted to have chosen Dominic for this year's Scholars Innovation Award. He is clearly incredibly capable, with exceptional engineering knowledge and attention to detail at this early stage in his career. He's enthusiastic, very able to communicate well, and EMSTA wish him well with his future career in engineering. Very well done. Thank you. Over to Dominic.
Right, I'd just like to say I'm absolutely ecstatic about receiving this, and it just feels like quite surreal that, I mean, all my hard work that I just put in like completely paid off in the end, because at times it just felt like I was just kind of doing work and nothing was getting recognised, but now everything's just kind of falling together, and it's really quite just like emotional, really. And I just really like to say that my deepest thanks go to Mrs. Atfield for like constantly inspiring me to always kind of push myself. So I just don't know really what to say, because I'm so overwhelmed, really. Yeah, so here's the award that I received.
Well, thank you, Amanda. And congratulations, Dominic. You are truly a most deserved winner of the 2020 Arkwright Scholarship. Our congratulations to you. Now, let's launch the Q&A session. Martin and I will lead that, and we'll start that now. Thank you.